Now let's move on to the second part of tutorial number 3, which is the optical properties of materials. Problem number 6. Problem number 6 says visible light having a wavelength of 5 times 10 to the minus 4 meters appears green. Compute the frequency and energy of a photon of this light. So let's first compute the frequency. So frequency, which is nu, is equal to c times lambda, where c is the speed of light and lambda is the wavelength. So the speed of light is a constant, which is 3 times 10 to the 8 meters per second. And our wavelength is 5 times 10 to the minus 7 meters. That's going to give us a frequency of 6 times 10 to the 14 inverse seconds or hertz. So we can conclude that our frequency is equal to 6 times 10 to the 14 inverse second, or we can say it's hertz. So that is our frequency, and the next thing we need to do is calculate our energy. So our energy is equal to hc divided by lambda, where h is Planck's constant and c is the speed of light. So substituting our values again gives h, which is Planck's constant, which is 6.63 times 10 to the minus 34 joules times second, times the speed of light, which is 3 times 10 to the 8 meters per second. And that's all divisible by lambda, which is 5 times 10 to the minus 7 meters. Plugging that into your calculator is going to give you 3.98 times 10 to the 19 joules. So we can say or conclude that our energy is equal to 3.98 times 10 to the 19 joules. And that's the end of problem number 6. Let's move on to problem number 7. Problem number 7 says, the index of refraction of quartz is anisotropic. Suppose that visible light is passing from one grain to another of different crystallographic orientation and at a normal incidence to the grain boundary. Calculate the reflectivity at the boundary if the incidence of refraction of the two grains are 1.544 and 1.553 in the direction of light propagation. So this is a very straightforward problem. All we have to use is the Fresnel equation. So the Fresnel equation says that R is equal to N2 minus N1 squared divided by N2 plus N1 squared, where N1 and N2 are the indices of refraction of the two surfaces respectively, and R is obviously the reflectivity. So just all we have to do is simplify this by substituting our values. So we can say that 1.553 minus 1.544 squared divided by 1.553 plus 1.544 squared is going to yield us a value of 8.45 times 10 to the minus 6. So for this system, we can say that the reflectivity is equal to 8.45 times 10 to the minus 6. And that's all we have to do for problem number 7. Let's move on to our final problem, tutorial number 3, which is problem number 8. So the indices of refraction of fused silica and soda lime glass within the visible spectrum are 1.458 and 1.51 respectively. For each of these materials, determine the fraction of the relative dielectric constant at 60 Hz that is due to electronic polarization, using the data in the table below. Neglect any orientation polarization effects. So the first thing we need to do when solving this problem is state our assumptions. So our assumptions are as follows. So our first assumption is that both materials are transparent. And our second assumption is that they have a very low magnetic permeability, which is mu r is approximately equal to 1. So with these two assumptions, we can now say that our dielectric constant is equal to our index of refraction squared. So now all we have to do is find our dielectric constant for both of our materials and then determine the ratio. So our dielectric constant for our silica is equal to 1.458 squared, which is equal to 2.13. And now we're going to do the same thing for our dielectric constant of our glass, which is equal to 1.51 squared, and that's going to yield us a value of 2.28. So now that we have both dielectric constants, to determine the ratio, all we have to do is divide it by the dielectric constant at 60 Hertz. So let's do our silica first. So for silica, we can say that our dielectric constant for silica divided by our dielectric constant at 60 Hertz is going to give us our ratio, which is just equal to the value previously calculated, which is 2.13, divided by our dielectric constant of 60 Hertz, which we're going to get from the table, which is fused silica and dielectric constant at 60 Hertz, which is 4. So we're going to divide that by 4, and that's going to give us a ratio of 0.53. Now we're going to do the same thing for our glass. So we can say that our dielectric constant for our glass divided by our dielectric constant at 60 Hertz, and that's going to give us 2.28 divided by, again, our dielectric constant for our soda lime glass at 60 Hertz, which is 6.9. And finally, that's going to give us a ratio of 0.33. So we can conclude that the electronic contribution, or the ratio between the two for both materials, for silica and glass is 0.53 and 0.33 respectively. And that'll conclude problem number 8, and that'll conclude as well tutorial number 3.